A train of proper length 85 meters moves with speed 0.6 c relative to a stationary observer on a platform. A. Define proper length. It's a length measured in a reference frame where the object is at rest. B. In a reference frame of the train, a ball travels with speed 0.5 c from the back to the front of the train as the train passes a platform. Calculate the time taken for the ball to reach the front of the train in the reference frame of the train and in the reference frame of the platform. This situation can be illustrated as follows. Let S be stationary reference frame relative to the Earth or to a platform, and S prime be moving reference frame relative to a train, and this moving reference frame moves with speed 0.6 c, and the ball is moving with speed 0.5 c relative to the train. And the first question, we need what time taken for the ball to reach the front of the train in the reference frame of the train, and since it's in the moving reference frame, it's delta t primed, and time is what is distance divided by speed. Speed is 0.5 c relative to the train, but what about the distance? It is given 85 meters, but it's a proper length, and where is it? We know that proper length is measured in a reference frame where this train is stationary, and this train is stationary in S primed, so it's 85 meters, and the observer, which is stationary on a platform in S, we will measure contracted length, which is 85 divided by gamma. Gamma should be calculated for this value of V, and it becomes five. In this one you can see that it becomes 5.7 times 10 to the power of negative 7 seconds, and the same time, but the time taken for the ball to reach the front of the train in the reference frame of the platform. And there are three methods or three ways to calculate this time relative to the platform, and the first is just use a formula. Delta t is delta t not primed. Why? Because it's relative to a platform in not primed reference frame, and formula says that it's gamma delta t primed plus v delta x primed over c squared, and is equal to gamma. Gamma should be calculated for v, which is 0.6 c, and it's 1.25, and gamma is 1 over root 1 minus v squared over c squared. Delta t primed, its time required in moving reference frame, and it's actually this answer, 5.7 times 10 to negative 7, plus v is 0.6 c. Delta x primed, it's 85, and in general delta it may be positive or negative since it is moving to the right, so it's positive. Notice that in general train can be moving to the left, but hence v will be negative, but delta x prime also will be negative. Why? Because it becomes to the left, so change in coordinates will be negative, and minus minus you get the same plus here, and divided by c squared, and it becomes this, and multiplied by gamma, so finally it's 9.2 times 10 to negative 7 seconds. The second method. For the second we need relative speed or speed of the ball relative to the platform. And we use special relativity formula. So we need speed of a ball in not primed, so we need u, and u primed is 0.5, and it's to the right, so it's plus, and v is 0.6. Our actually formula is u prime plus v, 1 plus u prime v over c squared, and hence it becomes 0.5 c plus 0.6 c divided by 1 plus 0.5 times 0.6 c squared over c squared, and you can see that it becomes 1.1 divided by 1.3, and it becomes 0.846 c. And now let's consider a train as stationary reference frame and a ball as moving reference frame. So it's 0.5 c, train is stationary. And now a ball or reference frame relative to the ball measures a proper time because two events occur at the same place, and time calculated relative to the train, it will be dilated time. And if you divide 5.7 times 10 to negative 7 by gamma, but what is gamma? Gamma should be calculated for 0.5, and it's 1.15. It's 1.15, and it's proper time. It's time in reference frame in which ball is stationary, or reference frame relative to the ball. And now let's consider reference frame relative to a platform or relative to the earth as stationary, and also reference frame relative to a ball. But now ball is moving with speed 0.846 c relative to a platform, and also relative to a ball. Platform is moving with the same speed but to the left. In general also may be required, but now and again, but time measured in reference frame relative to a ball is this time, and it's proper time. And time measured relative to a platform, it will be dilated time, but we should use gamma with this v, and this gamma is 1 over root 1 minus 0.846 squared we need to calculate it. One minus 0.846 squared, and you can see that it's 1.876, and the required time delta t becomes this proper. You may calculate, it doesn't matter, so it's 5.7 times 10 to negative 7 divided by 1.15 and multiplied because a platform or reference frame relative to a platform will measure dilated time, and we should get also what this answer, because we calculate the same. Let's check. So multiplied by 5.7 divided by 1.15, and you can see it's a bit different due to roundings, but you may write that it's 9.3, it's acceptable seconds. And the third method, if we consider a platform and a ball, or actually, yes, we consider a ball which is moving relative to a platform which is moving with this speed, what, 0.846 c, in a train which is moving with speed 0.6 c relative to a platform. Again, relative to a platform, ball is moving with speed 0.846. Why? Because it is calculated using formulas, because 0.5 is speed relative to the train, but we need relative to a platform, and a train is moving with speed 0.6, but distance is 85. It's what, relative to a train, but relative to a platform this distance will be contracted, and it will be divided by gamma. It's calculated for v 0.6, because the observer on a platform will measure contracted length over train. Why we take this? Because it's a moving reference frame, it's speed of this object, and actually we need what, length of the train and speed of the ball. It doesn't matter, we don't need speed of a ball to calculate distance of a train. And now for the observer on a platform, you can see that ball will move with speed, what, 0.846 minus c. It's clear because they are moving in the same direction, but a ball must travel distance which is 85 divided by 1.25. Let's check. Notice it may be a bit confusing. You don't need to use again special relativity formula. You just, because it is already calculated or taken into account when we calculate this. So here just minus, because they are moving in the same direction. So it becomes 85 divided by 1.25 and what, 0.246, and speed of light 3 times 10 to the power of 8. And you can see that it's 9.2 times 10 to the power of 7 seconds. And that's all for this question.